In 1868, a journalist from a publication called The Builder visited a new building in the marshes of East London. He was there to cover what the Metropolitan Board of Works was describing as a major public health achievement. He arrived expecting a utility building. What he found made him write the following sentence. And these are his exact words, published in 1868. The building seemed to be an elegant structure in a swamp, which might be taken for a mosque or Chinese temple, a mosque or a Chinese temple, in a London marsh. Built officially to pump sewage, the building is called Abbey Mills Pumping Station. It was designed between 1865 and 1868. Its architect, Charles Driver, gave it a Greek cross plan, Russian Orthodox octagonal domed lanterns, Italian Gothic windows, Flemish roof lines, Venetian brickwork, Byzantine interior ironwork, Celtic doors, 6 distinct architectural traditions, each of them historically associated with religious or sacred architecture, for a sewage pumping station. The official explanation is that the Victorians were proud of their engineering achievements and expressed that pride through elaborate architectural decoration. This explanation is offered, repeated, and generally accepted, but it does not answer the specific question that the building raises. Because if you want to express pride in an engineering achievement, you decorate the building that the public sees every day. Abbey Mills Pumping Station was built in a marsh in East London. It had no regular visiting hours. It served no public function. The people of London would never walk through its doors. So who was the architecture for? The man, A.N.D., the stench. To understand why Bazalgette built what he built, you need to understand what London smelled like in the summer of 1858. The answer is, it smelled like death. The Thames had become, by the middle of the 19th century, the largest open sewer in the world. 2.5 million people living in the most densely populated city on earth, all of them directing their waste through cesspits, through street channels, through direct pipes into the same river that supplied the city's drinking water. Cholera had already killed more than 30,000 Londoners between 1830 and 1855. Not in one epidemic, in waves. Every few years the disease returned. Every few years the poorest neighbourhoods buried their dead in mass graves, and the prevailing medical theory held that cholera was caused by bad air, not by contaminated water, by smell. Miasma theory, the idea that disease spread through corrupt air rather than contaminated water, was the dominant medical consensus of the era. It was wrong, but it was held by the most respected physicians in London, and it shaped every decision about infrastructure for decades. Then came the summer of 1858. The combination of an unusually hot June and the accumulated decades of London sewage began producing hydrogen sulfide gas from the river at concentrations nobody had ever experienced before. The smell reached the Palace of Westminster. Members of Parliament, the men who had been debating and delaying sewage reform for 30 years, found themselves unable to sit in committee. The curtains of the House of Commons were soaked in chloride of lime just to allow the building to be used. It became known as the Great Stink, and it ended the debate. Parliament authorised the Metropolitan Board of Works to begin the construction of London's main drainage system, immediately with adequate funding. Without further committee review, the engineer they had already appointed the man who had been proposing solutions for years, whose plans had been rejected by committees, delayed by costs, questioned by rivals, was finally given permission to build. His name was Joseph William Bazalgette. Bazalgette was born in 1819 in Enfield, North London. He was the son of a retired Royal Navy captain. He was, by every documented account, meticulous to the point of obsession, a man who checked and rechecked every calculation, who insisted on specifications his colleagues considered excessive, who built things not for the current moment, but for the next century. He had been working on plans for London's drainage since the early 1850s. He had watched cholera kill thousands of people while Parliament debated cost estimates. In 1858, he was given the authorization to begin. What he built, the scale of it, the decisions he made, and specifically the shapes he chose, is still operating beneath London today. And some of those choices have never been fully explained. The shape that shouldn't work. Most people, if asked to imagine a sewer tunnel, think of a circular pipe. Bazalgette's main intercepting sewers were not circular. They were egg-shaped. Specifically, they were built in the profile of an inverted egg, wide at the top, narrowing to a curve at the base, the widest horizontal dimension at roughly 2/3 height, the narrowest point at the bottom. The official engineering explanation for this choice is documented and real. The egg shape does two things simultaneously that a circular cross-section cannot. First, structural strength. An egg profile under compression from the weight of the city above distributes stress more efficiently than a circle. The load transfers through the curved walls in a way that prevents collapse. This is why eggs are so difficult to crush. The geometry converts pressure into structural tension rather than allowing it to concentrate at any single point. Second, hydraulic efficiency at low flow. London's sewers do not run full at all times. At low flow periods early morning, dry weather the waste moving through the system is a relatively small volume at the bottom of a large tunnel. In a circular pipe, this small volume spreads thin and slow, losing the velocity needed to carry solid material. The inverted egg creates a V-channel effect at the base. Even a small volume of liquid moves fast through the narrow base, fast enough to carry solids, fast enough to prevent the accumulation that would otherwise require manual cleaning. This is the official explanation. It is a good explanation. It is not a complete explanation. Because the egg cross-section does a third thing, something that the official engineering literature describes in passing but does not examine, something that anyone who has stood in one of Bazalgette's tunnels and spoken or simply listened to the silence notices immediately. The egg cross-section, in brick, at the dimensions Bazalgette specified, creates a specific acoustic environment. Not just good resonance, specific resonance. The geometry of an inverted egg, constructed in hard-fired Victorian brick using Portland cement, at the dimensions of Bazalgette's main intercepting sewers, roughly 6 to 12 feet in maximum width, produces a standing wave frequency in the range that acoustic engineers now describe as infrasound. Low frequency vibration, below the threshold of normal hearing, but not below the threshold of perception. Infrasound at 12 to 20 Hz does not register as sound, it registers as feeling. Researchers studying the acoustic properties of historic buildings' cathedrals specifically have documented that this frequency range produces in human subjects a sense of unease, awe, and heightened perceptual awareness. The Victorian engineer Vic Tandy discovered this effect accidentally in the 1990s while working in a laboratory in Coventry that staff described as haunted. He traced the reported phenomena feelings of unease, peripheral visual hallucinations, a sense of presence to a standing infrasound wave at 18.98 Hz, produced by a ventilation fan interacting with the room's geometry. His paper, published in the Journal of the Society for Psychical Research in 1998, proposed that many reports of haunted locations might be explained by architectural geometries that naturally produced infrasound. Medieval cathedral builders did not have acoustic engineering as a discipline, but they had centuries of empirical knowledge about which building proportions produced the desired effect on the people inside them. The cruciform plan, the barrel-vaulted nave, the specific ratio of height to width to length, the hard stone surfaces that reflected rather than absorbed. These were not aesthetic choices that happened to have acoustic effects. The acoustic effects were the point, and the academic literature on medieval sacred architecture consistently demonstrates that the specific geometric proportions used in Gothic cathedrals produce standing waves in the infrasound range as a natural consequence of their dimensions and materials. Now look at what Bazalgette's architect Charles Driver chose for Abbey Mills. A Greek cross plan. The same cruciform geometry used in Byzantine and early Christian sacred architecture for 1500 years. Built in brick, a hard reflective acoustic surface. With a central octagonal dome, a form that in every sacred tradition that has used it, from the Dome of the Rock to the Florence Baptistery to the Church of the Holy Sepulchre, concentrates and focuses acoustic energy toward the centre of the space. For a sewage pumping station. Charles Driver A-end the question he was never asked. Charles Henry Driver was not primarily a public works architect, he was a railway architect. His documented body of work before Abbey Mills consisted primarily of railway stations, buildings designed to move large numbers of people through transition spaces, buildings where acoustic management was a practical concern, buildings where the emotional and psychological experience of the passenger was understood to matter for commercial reasons. Railways needed passengers to feel safe, purposeful, impressive. Driver's railway stations were designed with those effects in mind. And then he was given a commission to design a sewage pumping station in an East London marsh. The standard historical explanation is that Driver brought his railway station aesthetic to the pumping station commission, that the elaborate decoration was simply his architectural language, applied regardless of building type. This explanation is offered by architectural historians and is not unreasonable, but it leaves a specific question unanswered. Railway stations are experienced by passengers. The decoration is for the people moving through the space. Abbey Mills was experienced by maintenance workers and pumping engineers. Nobody visited Abbey Mills for the experience of being in it. And yet Driver didn't just decorate it. He made specific structural choices, the Greek cross plan, the octagonal dome, the specific proportions of the interior spaces that had acoustic consequences. Choices that were not required by the building's stated function. Choices that used more materials, more labour, more cost than a straightforward industrial building would have required. The original specification for Abbey Mills, documented in the Metropolitan Board of Works records from 1864, included not only the pumping machinery, but the full architectural programme that Driver ultimately built, including the twin ventilation chimneys, 212 feet high, standing 212 feet above the East London marsh, richly ornamented, visible for miles. Official reason for the chimneys: ventilation. The pumping machinery produced gases that needed to be extracted from the building. This is documented and true. But ventilation chimneys do not need to be 212 feet high. Standard Victorian factory chimneys for equivalent ventilation needs were 60 to 80 feet. The additional 130 feet of height served no ventilation function. It served a visible function. And two questions that the official history of Abbey Mills does not ask directly are these. What was so important about this building's visibility above the East London marsh? And what was so important about this building being visible from, and visible as a religious structure, when the people who would ever see it were largely the people of East London who could see it from a distance? In 1868, the only buildings that rose above the East London skyline were churches. Abbey Mills rose higher than any of them. The unmapped miles. The London sewer system Bazalgette built has 82 miles of main intercepting sewers and 1,100 miles of street sewers. The system is still in use today, 160 years after its construction. Bazalgette built it with Portland cement at a time when most engineers were still using Roman cement, a decision his superiors at the Metropolitan Board of Works questioned as unnecessarily expensive. His documented response was that he intended the system to last 300 years and the cement would determine whether it did. He also built it larger than any calculation required. This is one of the most frequently quoted facts about Bazalgette's system. He calculated the maximum sewage flow the system would need to handle. Then, in his own words, he doubled it. When asked why, he said he anticipated London's growth would exceed any current projection. This is the official reason. It is also the reason the system is still functioning in a city of 9 million people that Bazalgette built for a city of 3 million. His doubling saved London's infrastructure from obsolescence. Every engineer since has described it as visionary. But there is a third consequence of the oversizing that the standard accounts do not examine as a primary question. If you build a tunnel twice as large as the calculated requirement, the acoustic properties of that tunnel change significantly from a tunnel built to specification. The resonant frequencies of a chamber depend on its dimensions. A tunnel built to Bazalgette's doubled dimensions produces standing waves at a different frequency than the same tunnel built to minimum specification. A larger chamber resonates at lower frequencies further into the infrasound range. Now, the documented acoustic anomalies of the Bazalgette tunnels. This is not speculation. This is documented. In 1993, Thames Water engineers conducting routine maintenance in a section of Bazalgette's main northern outfall sewer filed a routine maintenance report. The report noted, in its final paragraph listed as an observation rather than a finding, that the tunnel section from coordinates approximately consistent with the stretch beneath the latent area produced an unusual acoustic environment at low flow periods. Specifically, workers reported a low, sustained vibration perceived through the body rather than heard through the ears. No mechanical source for the vibration was identified. The report recommended further investigation. No further investigation was commissioned. The report is filed in Thames Water's infrastructure records. It has never been cited in any academic paper or engineering study. In 2019, a group of urban explorers accessed a section of the Bazalgette system that had been temporarily taken offline for maintenance. One of them, a musician and sound designer who publishes under the name Marcus Field, recorded the acoustic environment. His recording shows a standing wave at approximately 18 to 19 Hz, nearly identical to the frequency Vic Tandy measured in the Coventry laboratory, nearly identical to the frequency that acoustic researchers have measured in the naves of several Gothic cathedrals. Field published the recording on a sound design forum. It received 17 comments. Nobody followed up. The question this raises is not whether Bazalgette deliberately designed acoustic tunnels instead of sewers. The question is whether he was working within a tradition of infrastructure design that understood from empirical rather than theoretical knowledge the relationship between geometry and felt experience. A tradition that the official history of Victorian engineering has not looked for because it has not thought to ask. Crossness, AND, the geometry of the octagon. Bazalgette built a second pumping station at the southern end of his system. It is called Crossness. Abbey Mills was described by a journalist in 1868 as resembling a mosque or Chinese temple. Crossness was described by the architectural historian Nicolaus Pevsner, one of the 20th century's most respected voices on architecture, as a masterpiece of engineering, and a Victorian cathedral of ironwork. Those are his exact words. The Crossness interior is unlike anything built for industrial purposes in the Victorian era or any era before it. Red and green cast iron columns with Romanesque capitals carved with leaves, stems and fruit, the same plant motifs used in medieval ecclesiastical carving. An octanal central space whose proportions Pevsner specifically identified as Byzantine. Cast iron screens with the same geometric interlacing patterns found in Islamic sacred architecture from the 8th century onward. 4 beam engines, each weighing over 50 tons, given names. Victoria, Prince Consort. Albert Edward. Alexandra, not numbers, not mechanical designations, names of the royal family. The 4 engines of Crossness were the largest rotative beam engines built to that point in British engineering history. They were named for the royal family and housed in a space designed with the proportions and decorative vocabulary of a Byzantine cathedral. The official explanation: Victorian civic pride. The era valued the demonstration that industrial work had moral and cultural dignity. The elaborate decoration expressed that value. This explanation is offered, accepted, and repeated. It does not explain the octagon. The central octagon of Crossness is not decorative, it is structural and geometric. An octagon is the intermediate form between a square and a circle, the shape that medieval architects used as the transitional geometry between earthly square plans and heavenly circular domes. The mathematics of its proportions, specifically the ratio of side length to the span of the space, appear consistently across the sacred architecture of 3 distinct traditions: early Christian, Byzantine, and Islamic. The Florence Baptistery. The Dome of the Rock. The octagonal chapter houses of Gothic English cathedrals. The baptismal fonts of Romanesque churches across Europe. Octagonal spaces in sacred architecture consistently place the human being at the center of a geometry that, through the relationship between the dimensions and the hard reflective surfaces, produces a specific acoustic experience. The human being standing at the center of Crossness's octagonal hall in 1865, when the beam engines were running and the building was operational, would have been standing in the acoustic center of a space designed with the same proportional logic that sacred builders had used for 1500 years to create a specific felt experience. Charles Driver knew this. Whether he designed it consciously or whether he was, as a railway architect, working within a professional tradition of space design that incorporated this knowledge empirically without theorizing it, is the question the official history of Victorian engineering has not asked. Joseph Bazalgette died in 1891. He left behind 82 miles of main intercepting sewers, 1,100 miles of street sewers, 4 pumping stations, and 2 embankments along the Thames that reclaimed 22 acres of riverfront. He saved more lives than any Victorian doctor. His name is on a bust on the Victoria Embankment. His system is still operating beneath London today. And the specific question his work raises, why a man commissioned to solve a public health emergency built structures with the proportions and acoustic properties of sacred architecture, has never been the subject of a funded academic investigation. The official explanation is Victorian pride. It is not an adequate explanation for the Greek cross plan of Abbey Mills, or for the 212-foot chimneys built 130 feet higher than ventilation required, or for the Byzantine octagon at Crossness, or for the standing infrasound wave recorded in the Bazalgette tunnel at 18.3 in 2019, the same frequency measured in Gothic cathedral naves. These facts exist in the public record. They have not been assembled into a question, because nobody has funded the assembly. The system he built still carries London's waste beneath the streets of a city that has tripled in population since he built it. The pumping stations he built still stand Grade 2 listed buildings, nationally protected heritage structures. Abbey Mills is still operational. Crossness's beam engines are still being restored by volunteers. The question of what those geometries were designed to do beyond pumping sewage is still there. The tunnels are still there. The frequency is still there, waiting for someone to ask with the measurement equipment and the patience the question demands, whether what Bazalgette built beneath London was only ever what the official record says it was.